his work. He's a very active researcher and actually a very active person. So he studied, he graduated from Lviv Polytechnic University in 2009, I think, or 2008. Then he worked a little bit different projects and he traveled some. And then he did a joint PhD between the University of West Bohemia in Pilsen in the Czech Republic and the University of Rennes at the IETR laboratory. And he obtained his PhD in 2017. And then he moved abroad again. He went first to Belgium, Ghent. And then 1 year at the EPFL in Lausanne. And then he was recruited at CNRS as a CNRS researcher. So then we are in 2020. And so I already said he's very active, he has a busy schedule. He's also a member of the CNRS evaluation committee for the engineering sciences. So for those who know, it's section 8, which is perhaps one of the most interesting sections of CNRS if you're from Mécatronics. And all this to say that I'm very happy that Denys will present his work on wireless implantable bioelectronics, where you have like electromagnetic waves interacting with the human body and other obstacles. So, Denys, please.
Well, thank you very much. Hello, everybody. Thanks a lot, Martin, for this great presentation, for kind words, and thanks everybody for being here. So yeah, I will be speaking today, providing a general overview about wireless bioelectronics, theory, engineering, what we do in our group, and what this all about. So just a quick resume of what also Martin greatly presented already of my experiences. Maybe it's important just to know that my interest in wireless bioelectronics, it sparked around the age of maybe 6, when my father, who was cardiologist and also avid radioelectronics enthusiast, he showed me the very first implantable pacemaker from Medtronic. And for a 6-year-old kid, it's everything that needed to be done to define what I'm gonna do in my life. So voila, so here is a quick overview of the IETR laboratory. So we are located in the campus of Beaulieu in Rennes, here, just nearby. And we have in total, we have around 360 staff, from which around 150 PhD students and postdocs. So it's a big laboratory with the axis mainly in electronics, telecommunication, some security as well. So very, very interesting topics around electronics and numerique, how we call it here. From the equipment point of view, we are one of the best facilities in Europe, I might say, in electromagnetics. We have anechoic chambers, 8 of them actually, near field, far field, going for all range of electromagnetic frequencies from few hundreds of megahertz to terahertz, almost uninterrupted, reverberation chambers, and many interesting equipments, and even our own airplane, but it's not related to our projects. So yeah, I will be speaking quickly. I will first start with the theory, and then we will see some engineering examples, and then provide some summary and perspective what is going on in this field right now. So to start with, what is wireless bioelectronics? So it's a big field, very active right now, so it allows to interface with physiological processes and provide information about health or even actuate some functions. There is a lot of advancements right now. It's impossible even to do an overview in one single talk, but I would like just here mention some existing device classes. So there are neural interfaces you might have heard of, well, let's keep what Elon Musk is doing, but maybe focus on more therapeutic applications. Here, one like deep brain stimulation example, which is shown in this figure, is mostly to treat Parkinson's disease. You can even, maybe somebody of you already saw this fantastic videos of a person in a very late stage of Parkinson with big tremors. When we turn on the brain stimulations, the tremor instantaneously go away like magic. So this is really technology that provides great potential for many neurodegenerative disease. There are also pacemakers, as I mentioned previously in introduction, very useful technology, established one. There are also ingestible devices. Our group works on this type of capsules as well, so they can just provide some sensing inside of gastrointestinal tract. Usually the most common applications are temperature, pressure, but there are also endoscopy, so we can provide wireless video from inside of the areas that are impossible to image with other types of wired endoscopes. And of course, drug delivery, also implantable pumps for insulin, for cancer treatment, and many different applications. The problem with all of these devices, and actually here I mentioned only human applications, but also implantable devices are used a lot in animal research when we would like to study something that is going on in animals, in behavioral research or physiological or testing drugs to different applications. So the problem is, first of all, if we would like to have some high functionality, high data rates, very often wires are used. So for neural interfaces for animals, they are fantastic devices, but they are wired, which is, first of all, dangerous for infection. It induces huge stress on the animal, and we need complex surgery to implement them, to put them into place. So, of course, if possible, we would like to get rid of wires. And of course, for human applications, nobody wants the wires. So it's just, yeah, we try to do them wireless. And if we do them wireless, we need batteries to power them. And usually in modern devices, like the one I show here, the batteries, they take much more than half of the whole useful space. So sometimes up to 90–95% of the volume of the device are the batteries. So of course, this is very invasive. We need, again, the complex surgery to implement these devices. So we would like to get rid of that. And this is actually the mission of our team. So we would like to imagine some kind of application like this one. So the device, which is wireless, very small, batteryless, long-lasting, could be realized either conventional materials or biodegradable materials, depending on applications, can be delivered using a catheter, for example, to the application site. Then we have a wireless solution developed that automatically localizes where the device is and provides the powering, like something like RFID, let's say, but for the human body. And finally, the device interfaces with a physiological function and backscatters the measured signal. It's like remote sensing applications, but for the in-body application. And to make this possible, we approach this in two parts. So first, our lab focuses in theoretical studies of this phenomena in general of electromagnetic energy exchange with the human body, interaction of waves with tissues, propagation of waves in the tissues. And here, first we study the fundamental mechanisms that define how wave propagates in tissues, where the losses come from, and we quantify them. And based on these rules, then we also develop the optimal implantable radiating structures for both radiating energy or harvesting them. So they're safe, they're efficient, and they operate in the optimal operating scenarios. And we have also a very good network of collaborators. We are not alone, of course, doing that. And based on these studies, we also develop the existing solutions. So we know how to make them, so we also develop existing implantable devices, we characterize them, and we also do technology transfer, collaborate with companies. Notably, this one is a body cap company located in Con, and I'm very proud of this collaboration because these radiating structures developed in our team. They are used by NASA, SpaceX, by multiple sports teams, and etc. And finally, also another thing is when we make devices also very efficient already inside of the body, how to deliver power efficiently for them. And there also it's a project of my PhD student Ikaro, who recently defended actually his PhD, now is postdoc in our team, to study how to transfer energy to the deep body devices. And here we can feel already, we can see the first challenge. So when we increase the implantation depth or increase the miniaturization, our efficiency drops really significantly. And we can characterize a few different regions of operations of wireless power transfer for biomedical devices. The most common, the most used now is near field. So all of the devices I mentioned before with these big stages as pacemakers or neural stimulators, they contain this stage which is subcutaneous, quite large, and there we use near field transfer, like for mobile phone. Nothing goes better than that, nothing to do here, well, almost nothing. Some people will disagree. So, but if we would like to have a very small device, or if the separation distance between the device and like starts to change, it gets misaligned, and also the separation distance is larger than the cross-section of the device itself, we cannot use near field anymore. Well, we can, but it's very inefficient. So we start to work more already in the realm of waves. So that could be either just a few wavelengths which are characterized by the region of midfield, or it could be propagating waves already in far field. And we actually, with our team, focus in this region, and we would like to make these devices reconfigurable so we can, and bioadaptive. And by that I mean, so we will show later, we do not need to know where the device is located. We just put our solution, our radiating structure on top of the body. It automatically localizes where the device is, and it powers it just without any knowledge of what's inside. We don't need to do any imagery. So this could be very useful for applications. And in this context, we also try to study what are the losses, what are the optimal frequency, what will be the optimal type of the sources. So this is like this big type of the study. So let's now see a little bit contributions of our lab in terms of the theory. So this is the first slide. It looks very scary, but don't worry, I will explain. So it's just to show how the research usually works. We start with very simple models to understand like the physics of waves, the losses and everything. This is usually just a two infinite half space. We locate our source inside of it's our lossy medium, and on top there is a free space, and we try to estimate like what wave phenomena can we see in the separation of dielectric and free space. Then we add layers. We see what happens, how the layers affect transmission. Then we try to make like from two infinite half spaces, we make it cylindrical. We try to see what effects of the finite models of the body will introduce. And then finally, we simulate this numerically on realistic models, and we try to understand how all of these things that we learned on the simple models applies to the realistic models, and what are the effects. We can quantify them, and we can understand how to design now the sources, which will try to work on this only optimal things that favorizes the radiation and minimizes the absorption, which is actually absorption is also something bad we would like to avoid, because it causes this, as you heard, a specific absorption rate. As for mobile phones, the safety of the devices depend on this thing, so we would like to minimize it. And from here we estimate a few different type of losses. Of course, attenuation, you know, if any kind of wave propagates in the lossy medium, you will have attenuation. It will just get dispersed in heat. So this one, we cannot do anything with that. We can just find the region where it will affect the less. When we have also near field type of losses, near field type of losses is something which is related to the size of the device. It's difficult to explain quickly, but let's imagine if we speak about acoustic waves, it's if you try to produce a deep bass sound with a very small loudspeaker. It's a big simplification, but it's something like that. It's not going to happen. The device should be, in comparison to wavelength, sufficiently large to be an efficient radiator. So, and then we take like a trade-off between all of these mechanisms, and we can see what would be the most optimal scenario for like optimal frequency that finds a trade-off between these losses. And the most surprising things in this study that we found that actually most of losses happen because of the presence of this high contrast interface between human body and the free space. Just because the wave impedance is very different and we have this kind of lossy resonator, it accounts for 80 to 99% of total losses. So basically by removing somehow, by matching the wave impedance of the body to free space, we can greatly increase the efficiency of implantable devices and already get closer to get them batteryless. And this work, it provoked many follow-up studies in the field, and a collaborator and good friend of mine, John Ho, for example, proposed this interesting solution based on meta-surfaces. Maybe you heard about that. It's the surfaces with sub-wavelength properties that achieve some kind of wave manipulating behavior. And here, for example, if we put the meta-surface already on the surface of our body or just any kind of lossy dielectric, we can see that already we can improve by many times the transmission into the lossy tissues, but trying to minimize this interface. There's many methods. It's just one of the examples of how we can, by knowing what are the losses, we can try to overcome them. And second, now we know if we would like to do wireless powering, we can actually position our sources already on the surface of the body. And it's a little bit like ultrasound gel. We can match, we can provide this using some kind of matching medium to inject our waves in the body and avoid this huge area of losses. And here it's also a PhD project of my student Icaro, and he studied like this problem in from a very fundamental one with a very like simplified sources. Here it's with two different theoretical models. One is a realistic size of the implants, and here it's a simplistic source, but a fundamental models that can understand the like model superposition of the how the device actually radiates in terms of electromagnetic modes it excites, which is very important because we can study this near field behavior and understand it much better. And then also in the realistic model to quantify actually what it will be the maximum achievable efficiency. And the results were very surprising and very encouraging at the same time. It was, I would say, it was actually a breakthrough. Because if, let's say, we consider here a small pacemaker to which like 5 centimeters inside of the tissues, 2 millimeters in diameter, we would like to make it wireless and deliver this power without. So if we just use one transmitter, just one antenna, as we use currently in the field, you can see across the frequency what will be its efficiency. Like 10 minus 7, 10 minus 6, so very, very low. And you can see what will happen with the wavefront. It will get everywhere, will get just scattered, absorbed by tissues, and very little amount of energy will reach our target, which is right here. And then what Icaro actually is now developing, if we are trying to wavefront shape our energy to like do this some in different disciplines, we call it either beamforming, wave control, wavefront shaping. There are many words for that, but you can see we can provide this type of focusing right here, and we can improve our efficiency for the same scenario, same depth, same implant by 4 to 5 orders of magnitude, which is the main argument for our line of research in our lab, and we try to reach it. We now try to find a practical solution how to achieve this in practice. So there are many approaches. So I'd like to mention quickly one that we developed together at EPFL during my postdoc. It's just a fundamental approach that tries to understand how anything that radiates waves behaves if we put them on any arbitrary surface. So maybe you heard about like radars, phased array antennas, for example. Most of them are designed to work on the planar surfaces, and this is quite easy to compute. Now, if we would like to make our source conformal to any kind of object like human body, airplane, whatever, it gets much more complicated. Nothing fundamentally complicated, but yeah, the math gets much harder, and especially computing, how to compute it quickly. So this is the first approach we did based on this code. So if we just imagine our aperture positioned on the body, we can try to calculate what each of this point, it's one small source. And we can compute what should be the amplitude and the phase, which means like the strength of the signal, and also at which time each source have to emit in order to converge in our point inside of the space. But for these methods, we need the knowledge of where the source is, but usually we don't. So I will come back later to it. Then there is also part of studies that we do into how do we inject like maximum amount of energy in realistic scenarios into body. And we study these buffering layers. So we try to find which electromagnetic properties of our medium, of our, let's say, ultrasound gel for electromagnetic waves, we can use to inject the maximum amount of power, which is also very applied but very interesting project. And we also found some interesting this periodicity insights of how this material should be designed, and we also validated experimentally. Another project, also in collaboration with the CNRS researcher Julia Sacco and our common student Pratik, we also study different type of antennas for this region. Because if you would like to now, like I mentioned before, the radars and phased antenna arrays, for this one, each individual antenna has to be supplied with individual feed, with individual like line that provides the amplitude and phase control for each element, which is, can you imagine, very difficult to do, and especially if you would like to put them on the body and make portable. And this type of antennas, actually, they can scan in this axis, in the H-plane, which is noted here, just using the changing frequency of the antenna. So this is also one of the applied research. And then this structure is based on the special engineering, like this transmission line, so the part of the energy at each how to say that, meander, the energy leaks into free space. And we engineer this leaking of energy into something that's called leaky wave antenna. So it radiates in a prescribed manner. But we can also engineer the structure differently to confine the fields. And this is also work together with John Ho, he's the leader of this project, to confine the waves now, not to radiate them, to confine in most efficient manner close to the human body. And here in this recent paper with John, we proposed this very interesting technology. So let's imagine we have a scenario of two implants that needs to communicate. And if we just make to communicate them directly without anything, we can see that all of the fields will get dissipated very quickly in the body and almost nothing will reach something like right here, like the other part of the implant. And if we provide this type of the wave controlling structures, meta-surfaces, let's say, on the surface of the textile, we can greatly improve by a few tenths of dB the transmission between two of them. So it's really also very beautiful engineering by the team of John to design this type of devices. And finally, also another interesting application of wavefront shaping, also in collaboration with Julien Modelot from LTIC, also here in Rennes, and our student who also recently defended, Gabriel Gauguin, is to apply this to transcranial brain stimulation. So Gabriel focused in his project on the low-frequency stimulation. It means that our brain, you know, there are brain waves, they operate into kilohertz, hertz to kilohertz range, mostly hertz. And sometimes by non-invasively targeting this area, if there's some condition, it affects the firing rate of the brain, we can try to re-stimulate it and recalibrate it to the frequency it should work on. And yeah, so there's like, that was Gabriel's project on this thing, but then we thought, okay, can we use higher frequency like that? And if we use higher frequency, we can also focus energy mostly to the like deeper regions of the brain and provide higher focality also to do it better. A little bit like the final few words about the theory. Also, a big chunk of our work was dedicated to understand better how the implantable sources perform. And also important remark here that electromagnetics, if it's linear, and human body is linear, if we don't heat it too much, but we don't, we hope, and it's reciprocal. So it means if the antenna is a good receiver, it's a good transmitter and vice versa. And so here in this study, we understand how to design the optimal sources, to achieve the optimal radiation conditions for body implanted capsules. And here we study how, in terms of the depth in the tissues, size of the device, radius, even dielectric materials used for it, and type of antennas that we use, also electric or magnetic one, which type of the properties we can achieve. We can also study what are optimal currents to induce, like many different interesting things. And here there was another very big surprise for the field that actually we noted for the first time that electric sources could be much more efficient in than magnetic ones in human bodies. And here it's a bit surprising. Well, it's maybe requires a bit of explanation because everybody thought, look, like human body, it's a non-magnetic medium. It has like mu of relative permeability of equally 1. And high electric losses. So everybody thought like, yeah, let's put magnetic antennas right there. It will be very efficient. So it was common logic and very difficult to verify, but somehow papers reported efficiency that were comparable. And when we did this theoretical comparison of two different sources, we actually noted that the electric antennas, what is denoted here TM10, can achieve like twice the efficiencies. And the explanation for that is actually that body also have very high permittivity. At this frequency is about 50 to 60, the muscle tissues. And in this term, if we put our object, like our antenna, which is like electric radiator in this type of applications, into this lossy medium, it acts as a lens. Actually, it increases the electrical size of the antenna by the factor of square root of like effective permittivity, which means by a factor of 7 to 8, which actually shows this very good results. And we can also see different insights. For example, here, the antenna stops radiating at lower frequencies because, as I mentioned before, it's inefficient radiator when it's electrically small. Again, like a bass with a small speaker, not gonna work. If we go to higher frequency, then just the attenuation kicks in. The field will attenuate before reaching to boundary. And we have this optimal region when just everything just resonates and radiates everywhere, the things we try to achieve when we design actually the implantable antennas. We also use different models. We have like a good collaboration with the PFL in spherical wave expansion type of the models, and then also our models also based on like axial symmetry, higher order finite element methods, and also these models fit very well in predicting the peak radiation efficiency for the sources. And also, last interesting example published, just freshly published by our collaborator, Professor Anja Skrivervik. It's something about spherical modes. So maybe you saw already many times like the orbitals of the electrons. They are described as spherical harmonics. And basically, antennas can also be described by spherical harmonics, the things they radiate. The most simple radiation of the antenna is a dipole pattern, and then when we try to do more and more directive, we actually stack up the spatial harmonics. And we thought, okay, if the implant is inside of the body and we do it directive, we can maybe improve like twice the radiation efficiency, right? Or the gain in these terms. Actually not. Because whenever we go into higher order harmonic, here on this axis, we can see the distance of near field of the antenna. And the higher we go into harmonic, the deeper near field actually interacts with tissues. And what is the near field is difficult to explain. Some of you might know in a few words, but basically it's a region of the antenna where the wave is not yet radiating. It's kind of electromagnetic field that they interact, it's a mass, and then it produces a wave front on the boundary of the near field. What is important to understand that in near field, the losses are about like, it's a power of 6 as a distance. And well, it's difficult because we are in lossy space, but just to mention quickly, the losses are much higher in near field, basically. This is why we would like to make the antenna omnidirectional if you radiate in body. And here, finally, I'd like to show just a few engineering examples we do in our team. So we try to design now with all of the insides, the very efficient antennas with a specific size and specific radiation patterns. If you maybe heard about patch antennas, we designed the antennas which have followed the very similar distribution of the electric field, and it turns out that this simple antenna design provides the best efficiency for our type of applications. We made a series of them for any open frequency, depending on the depth, depending on the microcontroller you're using. And we also do experimental validation. We can see that these curves, they represent how well the antenna accepts the signal to be radiated. So it's called matching. It should get below -10 dB here. So we can see that these antennas operate very well in the intended band and also in any tissue. It's also important because if the tissues, they change their electromagnetic properties, different tissue, different properties, different humans, different properties, and the antenna should stay robust. And it's important to understand that we should stay below this value, and the antennas do stay. And we compare them also to fundamental bounds, and we can say that they approach closely the fundamental bounds in the efficiency, and they were so efficient compared to state of the art that they were also used in large animals also for animal telemetry. It's a collaboration with the University of Ghent, ongoing one, and it showed you that actually the efficiency can solve big problems, that now we can also provide telemetry, and they did this study using horses and cows actually. And finally, another engineering example in collaboration of National University of Singapore and EPFL as well. In this case, we made the antenna that resonates simultaneously in 2 bands. That, for example, one band can be used for harvesting wireless energy, another band for the data transmission. Same, it stays robust in all tissues, again, should be below -10 dB in these gray zones. It is, except for fat, but it's still quite okay. And this antenna has interesting feature also of reconfigurability. What it means? Let's say we cannot change the position of our receiver, neither the transmitter. And somehow, if we have this dipole-shaped pattern, because antenna, it's like electromagnetic field, it's a vector field, we will also have somewhere 0 of the radiation. And let's say by some big misfortune, our antenna is oriented to our transmitter exactly where the 0 is, and we cannot reconfigure it. We cannot change this position mechanically. So what we can do with very simple switch is just to rotate this pattern. And we can see it right here. So going from 0 to about -40 dB is actually quite good achievement. It's a demonstration. It does that at both bands, and it also stays at both bands quite close to the fundamental limitations. And the final example is the example of the technology transfer that we developed together with the body cap company. We designed the antenna that can be used in any type of tissues, or can be used as ingestible in humans or subcutaneous in animals, chickens, for example. So going from fat to stomach, it's very different electromagnetic properties, so it was a big challenge to address. And we did in our lab the entire wireless stage, like a RF circuitry, going into microcontroller, matching and everything, resonators right here, and the antenna itself. So here's the example of the prototype with the capsule of this size. I can show you after during the break, and yeah, quite proud of it. As I mentioned, it's used by NASA, SpaceX, and many different sport teams. And now the ongoing project with this company is something that really I'm very passionate about. This one, it's as I mentioned before, the antenna gets detuned as the function of the electromagnetic properties outside. And in gastrointestinal tract, the properties change in quite deterministic manner between different tissues, and we can use this to track where the antenna is located. There are some kind of disease of conditions can be diagnosed with this one, for example, gastroparesia, or it could be also endoscopic capsules that turn on their camera just in small intestine, let's say. There is many, many applications for this technology, and we also did our first test in animals already. It works really well, and now it goes into the already preclinical tests, I hope, by the end of this year. And very final example how the theory merges with technological translation, I managed before the spherical harmonics, how by the higher spherical harmonics will couple more to surrounding tissues. Actually, in this context, it's to our advantage, because you would like to use the antenna of the sensors. We can engineer the superposition of different spherical harmonics in such a way that our antenna is sensitive just enough as we wish to the surrounding tissue. So yeah, just to conclude, so there is a very big potential in bridging the gap between wireless wave control theory, wireless engineering, and biomedical engineering. By understanding physics of waves inside of the body, we can reach the unseeing efficiencies like before, which will enable a lot of different applications, battery-free applications, and generally improve the healthcare, improve the animal research as well, and reduce the need on the surgery, on the suffering of the animal, and many different advantages. And in our group, we address, like, first of all, the theory, but we also design the devices to realize these optimal parameters. And while we know already the optimal parameters, we also design the structures, how to interface with these devices in the most optimal terms. We also do in our lab all of the tests in what called laboratory phantoms, are the physical models of heterogeneous tissues to understand how the antennas interact with, the transmitter interacts with the receiver without needing to do this experiment on animals. We would like to minimize and reduce the usage, of course, of the research animals as much as possible. And finally, when we already do some kind of translational application, when we have our sensors on board, which can be used for the research or for medical applications, we need to show that in animal models. So that's a very final stage of many different of our projects to show that, yeah, we can indeed sense something that was not possible before and doing it now wirelessly. So yeah, I would like to thank all of my team for this fantastic work and all of the funding organizations. So here I would like to conclude and would be happy to answer your questions.
Thank you very much, Denys. A very complete overview of how to get electromagnetic energy into the body and how to get the information out. I will start with just a more general question. You showed some examples, I think. So on one side you have the electromagnetic simulations that show how the electromagnetic field is distributed, how it propagates into the body, or how the energy is transferred. I can imagine that it's quite challenging to validate these simulations experimentally. So can you give what kind of measurements can you realistically do? What kind of measurements would you like to do? So can you give some information on that?
Thanks a lot. That's a great question, Martin. Yes, indeed. So we try to simulate from the simple models to the most complex models, as I mentioned, to understand like what would happen in realistic body. It's very difficult to measure in our bodies, indeed. So we try to develop the fundamental models, like, for example, a spherical model, because it's very easy to compute. For the spherical model, we can also estimate the fundamental bounds. And we also have this like very small, like behind this foam, which is transparent to electromagnetic waves, we have a sphere. So we can also, our developed antennas, we can put them here and also estimate what will be the, like to compare the radiation performance of these things compared to our calculations. And if they match, we can, with some assumptions, we can understand that it will be the same in the body. So we can increase the efficiency.
Okay, so like this kind of model
Yes, for the antenna, for the on-body sources, it's slightly easier because they go on the body, so we can use, again, the phantoms, but which are just like the surface with reproducing electromagnetic properties. So yeah, there are some tricks to make.
Yeah, I can imagine. So, if you want to ask, please.
Hello, I have a few questions. I'm sorry for my
On peut parler français en fait. Oui, c'est juste. Oui. Oui, j'ai oublié de mentionner, pardon.
Je comprends pas mal, ne vous inquiétez pas. J'ai une question
C'était super.
sur les fréquences utilisées. Notamment, je vois sur, si je me souviens bien, la diapo 9, vous utilisez des fréquences à 2,4 GHz à peu près. Mais ça correspond à peu près aux fréquences d'excitation des molécules d'eau. Et est-ce qu'il n'y a pas des problèmes de compatibilité biologique entre les puissances émises
Oui.
et les effets potentiels des ondes sur la santé?
C'était une super question, merci beaucoup, parce que j'ai tellement de choses à dire dessus. Bref, oui, comment commencer? En fait, justement, toutes les fréquences qui sont supérieures, je ne suis pas spécialiste dans ce domaine, donc je ne vais pas mentir, mais au-delà de, imaginons, quelques centaines de kilohertz, tous les effets sont considérés aujourd'hui dans la communauté comme non comme thermiques. Donc, tous les effets nocifs qui peuvent y avoir sur la santé, comme les téléphones portables et tout ça, c'est les mêmes mécanismes qu'un micro-ondes, que ça va chauffer les tissus, notamment. Donc, justement, tous les dispositifs qu'on développe ici, ils sont sujets aux mêmes contraintes. Il faut que le débit d'absorption spécifique soit inférieur à une certaine valeur pour que les tissus ne soient pas chauffés. Sur le choix des fréquences, notamment, plus le tissu est chauffé, plus il y a des comment ça s'appelle, interactions justement, des absorptions. Donc c'est là où on veut surtout pas émettre. Et notamment, je pense que même les compagnies qui fabriquent les micro-ondes, ils ont fait cette grosse misconception. Parce qu'en fait, à 2,45, ça représente presque une fenêtre de transparence pour l'eau. Et en fait, parce que si on imagine, et c'est très logique, parce que si on met une pomme de terre qui a plein de l'eau dans la micro-onde, on veut la chauffer dès l'intérieur. Et pour la chauffer dès l'intérieur, il faut que les ondes, justement, ils peuvent aller partout, en fait. Que la pomme de terre, elle soit presque transparente, qui ne sera pas le cas si l'absorption, justement, sera locale sur la surface. Donc ça, c'est aussi une des misconceptions, et notamment, justement, ça se fait par juste dissipation, justement, diélectrique, l'oscillation et relaxation des molécules d'eau, où l'énergie est transférée en chaleur. Donc pour nous, c'est le même cas, mais les puissances sont beaucoup plus petites, et notamment, on voit que nos pics d'émission, justement, c'est vrai que le pic de performance, c'est notamment autour de ces fréquences. Mais ça, c'est un petit peu la coïncidence, parce que les tailles des objets qu'on met dans la micro-ondes, c'est parfois similaire aux tailles des organes, et la fréquence optimale pour aller le plus profond possible dans ces tissus, c'est autour de, effectivement, les régions de gigahertz.
Autre question?
Bonjour. Au début de votre exposé, vous avez mentionné le fait que les batteries occupaient 80 à 95% du volume. Et ma question est donc la suivante. Est-ce que vous envisagez de complètement retirer les batteries ou d'en garder quelques-unes de toute petite capacité et de recharger plus régulièrement à l'aide de...
Oui. C'est une super question, oui. En fait, même dans les applications actuelles, telles que neurostimulateurs ou stimulation cardiaque, ces dispositifs sont déjà rechargeables. C'est rechargeable par les champs proches, mais ils sont très grands et ils nécessitent aussi des chirurgies très complexes pour les mettre en place. Et après, ça dépend des applications. Donc, dès qu'on peut, bien sûr qu'on essaye d'éliminer les batteries. Notre rêve, un petit peu, c'est faire les dispositifs biodégradables. Imaginons, on fait une chirurgie profonde dans le corps. Il faut mettre un dispositif qui va suivre la guérison de certains organes ou son adoption par le corps. Donc, on met juste un dispositif qui est complètement biodégradable, qui est juste le métal et le diélectrique biodégradable. Et on peut juste l'interroger de l'extérieur avec ces systèmes de transmission d'énergie sans fil, avoir notre réponse un peu comme RFID. Et le dispositif, un an après, il va complètement être résorbé par le corps. Et donc, ça dépend, il y a tout. Il y a entre les recharges de piles et jusqu'à les dispositifs complètement passifs. Ça dépend des applications, des capteurs, des besoins d'énergie.
Du coup, dans les applications que vous développez, vous, il y a toujours des batteries, mais vous étudiez la recharge à plus longue distance pour avoir une chirurgie moins invasive.
En fait, on travaille plus au niveau plus physique, donc on essaie de proposer les solutions qui vont à la fois permettre soit recharger, soit complètement alimenter sans fil les dispositifs, via ce contrôle des fronts d'onde dans les milieux biologiques, qui va faire possible de meilleures performances pour les deux types d'applications. Voire certains, même mettre possible certains types d'applications qui n'existent toujours pas parce qu'il n'y a juste pas suffisamment d'énergie qu'on peut délivrer dans le corps.
Il y a aussi une question là, toujours d'actualité?
Oui, mais je pense que c'est plus ou moins répondu.
Ok.
remarqué que certains robots sont utilisés dans le corps humain afin d'agir directement ou passivement. Je pense notamment à des robots aux États-Unis qui servaient à enlever des fils qui étaient une curiosité pour les Américains. Et je me demandais si vous travaillez aussi sur ce type de robots qui, du coup, étaient en théorie réutilisables et qui sont, je pense, dans le domaine de recherche, vu que c'est dans le corps humain et que c'est ce qui est. Et du coup, je ne sais pas si vous travaillez là-dessus ou si.
J'ai juste pas compris le début de question. Donc, il y avait les piles rechargeables dans les robots.
En fait, c'est des petits robots qui travaillent dans le corps humain, qui sont censés être réutilisables et du coup qui sont sans fil. Et je me demandais si vous travaillez là-dessus.
C'est quelque chose qui nous intéresse beaucoup. On n'a pas encore les projets en cours, mais notamment, il y a beaucoup d'applications pour ce type de technologie, notamment ici, ce que je montrais, ce type de transparent. C'est lequel?
Dans ce cas-là, j'imagine qu'il faut mettre un actionneur à l'intérieur.
Oui, c'est ça. Notre équipe, on ne fait pas ça du tout. Donc, on ne travaille pas sur les actionneurs, mais on peut délivrer l'énergie à ce robot pour justement les alimenter. Et notamment, ce type d'approche qui est basée sur wavefront shaping. En fait, cette approche, elle est complètement agnostique par rapport à ce qu'il y a dans le corps humain. En fait, cette approche qui juste illumine tout le milieu de cette manière-là, qui écoute la réponse, et après, il sait exactement où le dispositif se trouve. Et ça, on peut le faire avec la vitesse de lumière, en fait. Enfin, c'est limité par l'électronique. On peut le faire 50 fois par seconde. Donc, en fait, si le robot se déplace, cette rayon-là, qu'on peut voir ici focalisé, on peut le faire, hop, en fait, déplacer vraiment, suivre le robot et l'alimenter de la manière la meilleure possible. Oui. C'est une longue question, ça répond un petit peu tout ce que je viens de discuter. En fait, cette antenne, elle peut être complètement conforme. Je vais peut-être prendre un peu du temps pour... Enfin, pas beaucoup, pour expliquer comment ça marche. Parce que imaginons que pour comprendre comment le wavefront shaping ça marche et pourquoi on n'a pas besoin de connaître les milieux, imaginez que ce dispositif il rayonne. On veut le faire passif, mais imaginez pour un instant s'il le fait rayonner. Donc il fait rayonner une fronde d'onde qui va propager partout et qui va être reçue par les petits récepteurs à l'extérieur du corps, qui vont être transmetteurs après. Donc sur chaque récepteur, on aura une amplitude, une phase de signal. Et donc maintenant, si on fait ce qu'on appelle time reversal, renversement temporel, et on va réémettre avec la même amplitude, mais avec la phase conjuguée, toutes ces ondes elles vont se converger exactement vers l'endroit où vient cette source-là. Mais maintenant, on veut que la source soit passive, donc on fait l'ingénierie de cette source-là avec les propriétés des ondes très spécifiques, que quand on l'illumine comme ça, il fait une backscattering, la rétrodiffusion des ondes, et en fait, cette rétrodiffusion des ondes, elle va contenir exactement la même information pour faire ce type d'ajustement de wavefront shaping. Donc, ça prend tout en compte. La forme de l'antenne, c'est ce qu'il y a à l'intérieur du corps, et donc c'est automatique. Les antennes qu'on design ici, oui, c'est résilient. Ça peut être les matériaux flexibles, bien sûr. C'est un peu dans la conception d'antennes, on prend en compte les déformations possibles. Par contre, et aussi, c'est une très bonne question parce qu'il y a pas mal d'approches de energy harvesting par piezo ou par électrochimie. Il y a beaucoup d'approches. Et aujourd'hui, ces approches sont très très bien, mais ça délivre l'énergie de niveau des microwatts, par exemple, qui est suffisant pour certains types d'applications. Mais nous, avec cette méthode-là, ce qu'on calcule, qu'on va être capable de délivrer à partir de 10 milliwatts jusqu'à 100 milliwatts si on est vraiment très bien. Donc on peut voir certaines complémentarités de ces approches même. Merci.
Bon, merci aux personnes qui ont posé des questions et merci à la... Merci beaucoup.